Good morning, everyone, and welcome to my talk. And actually, thanks a lot for Tom for a very nice introduction to the topic. And it's actually whether it was a coincidence or something organized by Tommy and the team. Anyway, good introduction for this talk. So in my talk, what we will go through is take one of those swimming lanes that Tom was describing and actually just going deep, going all the way to the bottom and counting the tiles on the bottom of the swimming pool of that particular swimming lane. There's a lot of stuff to cover, so I'll try to have some introduction on the topic first because it's quite obscure, even for the people who are familiar with these things. And then, going through how you can actually get started with this stuff and what can you do with these things. A few words about myself. About a decade in cyber, focusing mainly on the obscure topics. So all of the things that Tom also mentioned, stuff where you don't get any kind of manuals, where the vendors are very reluctant to give you any kind of information. So yes, all of those, that's my bread and butter. So let's start with very sort of brief introduction to the topic. There's a lot of acronyms in my presentation. There's a lot of stuff that you can't really abstract away. So I thought that we'll just get started with some very brief, this sort of university first class introduction to 5G and LTE. So the full architecture and the full system, whether it's 5G or LTE, it is complex. I mean, there's a lot of, as you can see, and this is just like very nicely abstracted way, the main components of the system. But yeah, there's a lot of stuff. And there's a lot of attack surface. There was, Tom also mentioned SS7, and there's a ton of protocols that are happening inside this, what's called a core network. But in this talk, what we're looking at is the yellow box on the left, which is the RAN or radio access network, and that's the sort of the last mile. And this is the thing that is basically the radio network that is connecting your equipment or UE or user equipment in this telco lingo to the what we in normal speak call the base station. But in this telco lingo, it's called G node B in 5G and E node B in LTE. And there's abbreviations, as I mentioned. So there's going to be a lot of these UE, GNB, ENB. These are used quite frequently throughout the slide. So good thing to remember those. So simple, the base station is the G node B or E node B. UE means your phone, any kind of embedded device that has a baseband radio or any kind of device really. There's also some other terms, for example, CP. That's the communication processor or the baseband processor. I use terms CP or comms processor or baseband processor. I just use them quite interchangeably. So if you hear any of those terms, what I mean with that is the actual chip that is handling the radio communications for that particular device. But yeah, so that's the focus of this presentation. Now, Tom talked about the swimming lanes, so I thought it's actually good to get this basic understanding what the radio access network actually is. So between the user equipment and the base station, we have actually two channels. So the downlink channel is from the base station towards the user equipment, and then you have uplink channel, which is the other way around. And both have a pretty wide bandwidth. So yeah, if we compare that to the crane radios, for example, that's very narrow bandwidth, whereas with these very high bandwidth, a lot of data that can be transmitted, so you need wide bandwidth. Each of these channels is split into two planes. So you have the control plane, And in the control plane, there is all of the signaling information, all of basically the stuff that the network requires to operate. So that's you have all of the stateful stuff there. So you are connecting to the network. All of that interchange happens on the control plane, and then you have the user plane, and that's where all the data is. And these are split into two planes to be able to, for example, if you have a voice call, you want to have very predictable delays on the packets, so that you're first getting this large delay when you hear back the voice, or that you get the Mickey Mouse voice where you all of a sudden you get a lot of data and then there's nothing. So you can do more control stuff on the control plane, and the user plane it's just like data where latency and stuff doesn't really matter. So if there's differences or jitter in the latency, it doesn't really matter. Some really interesting things have evolved quite a bit over the past, I would say, 5 years. There's a lot of research that has been conducted in the universities and in research institutes around the world for these baseband networks. And because of that, and partly due to that, we now have multiple open source implementations of these baseband radio access networks. The most well-supported and prominent ones these days are the Open5GS or SRS-RAN. It's basically, so the SRS-RAN is the LTE version of the Open5GS, but they can be used in the same host. And then you have Open Air Interface, which is another one. The code base is quite large, but they are actually really, really easy to set up and work on commercial radio. Tom mentioned some of these SDRs or software-defined radios, and you can actually run this baseband network on some of these. You will need, you can't go to the very low-end ones, so you will need a bit more expensive ones, like the Lime RF or Blade RF, or if you are swimming in cash, you can go with some of the Etus stuff, but they are quite expensive. So that's the university crash course, five student points in 2 slides. So let's look at how you can actually build. So first of all, to be able to interact with some of these devices, you need to have a network. I mean, you need SIM cards, you need radios, you need stuff. So what does it look like? It's not terribly exciting. It's not a massive rack of devices. It's just like it's a computer where you can run everything in a single host. So here I've specifically mentioned Intel x64, and that's because Open5GS and Open Air Interface, they are both optimized for Intel specific architectures because of some of the microcode that Intel is using. So yes, it works on ARM-based stuff and a bunch of other things, but it works best on Intel x64. So yes, you need a computer, you need a radio. Here I have a Blade RF. Then there is this gray box that says GPS DO. What I've learned running these rigs for a long time is that even if you get some of these really expensive radios, there's going to be drift on the clock of the radio. So you need something to maintain a very accurate clock signal for the radio, which means that you need a GPS-based oscillator to give you that accurate clock that is accurate. Like if you want to run this for a long time, and when you're doing fuzzing, you typically want. So you need an accurate clock that is constantly updating. So what this gray box is doing is that it's querying the GPS system for the time signal and then constantly updating the clock on the device and making sure that I'm getting nice and stable clock. Then something that Tom again mentioned already on his talk, which I can't emphasize enough, is that this stuff is illegal to do if you are not shielding properly. So you're operating in licensed bands So you're operating in the same bands where your normal cellular network operators are operating. So if you transmit, you're probably going to cause some harm for the actual operator, and yeah, at least in Finland that's illegal. So you will need some shielding. And here I have this pouch that I have been using, and I've been using some attenuators on the radio as well. So I don't need the antenna is 2 centimeters from the radio, so I don't need a massive signal power. So I can get everything nicely contained within the RF pouch. Why the pouch? It's just cheap. Like that's the cheapest way to do it. And radio signals are quite interesting and funny. So you can see that I have a USB cable going to the phone because you need to interact with the phone some way. Of course, when it's in the pouch, you can't open the pouch, but you need some way to interact with the phone. So I've been using, for example, with Android phones, I've been using just like screen copy and ADB. And when you run USB cable into the pouch, if you just run it straight through, you will leak the radio. The signals they don't contain within, like if you have a tiny gap somewhere, you will get the signals out. So here I have a shielded USB cable. I've cut the shielding or exposed the shielding, and I've grounded it to the actual pouch. So it's within the sort of same shielded domain, and I don't get any RF leakage out of the RF pouch. But it's still like if you are actually attempting this, it's a good idea to put your SDR into the box and then do some measurements, like very wide band measurements, to see if you are actually leaking any signals into the box. So you can measure it inside the box and see if you can capture any of the signals. If you can't, then you need to adjust your setup a bit to make sure that you're not getting. And I'm just emphasizing this again because like I said, it's illegal. Yeah, and last but not least, you have the target UE. So any kind of device, and depending on the devices that you're looking at, that defines the size of your RF shielding. If you're looking at these like massive equipment, then you need a bigger pouch or bigger case for those. Here's my setup. For the bare minimum stuff, you can actually the most expensive components are the RF shield and the radio. The rest is pretty cheap, to be honest. Anything and everything can be bought off basically any electronics retailer, Amazon, whatever. This is not like some hardcore military stuff that you need to have some special permissions to buy. You can just order them from Amazon, most of the stuff. So I have 2 separate setups. I have the Open 5Gs and Open Air interface running on different hosts, and I have 2 specific setups. And the reason for that is that although they should be standard compliant, like they should follow the standard, and there's a specific ways that you do things, there are still differences. I mean, standards, as everyone knows, standards are standards. So there's a lot of things that you need to interpret between the lines, and there's you can't get all of this information into the standard. So I'm running both purely because of that. But having this kind of setup for roughly 1,000 euros, and if you don't use the RF shielding, it's like 600 euros. It's quite a little money compared to what it was like 5 years ago, when you would have to go and actually buy some commercial second-hand equipment or a rack or massive rack of equipment that would be like hundreds of thousands of euros. And even today, the cheapest sort of ready-built 5G or LTE boxes that you can buy, like these standalone network boxes, they are roughly 8,000 euros, I think the cheapest one at the moment. But you can build effectively the same setup for a lot less. Now, what's inside the hood? So as I showed, there's one computer running this whole thing, but this is roughly what it looks inside. So everything here inside this lightish yellow box, that's running inside this Intel based computer running Linux. And the main components are, of course, the Open5GS or Open Air Interface. So this is the open source implementation of the radio access network, and they also provide implementation for the core network. So there's implementation for the EPC in the LTE lingo, or the it's a Dockerized version in the 5G. So yeah, that's running as its own component. Then you have the SDR drivers that are actually talking to this radio or this radio access network stuff. So the Open5GS Open Air interface, they are creating the packages, sending it to the SDR driver, and the driver is pushing it to the actual radio, which is then transmitting it to the actual equipment. Now, if you just want to run your own private LTE or 5G network, the stuff you need is basically right from this middle point. And then the left, that's the stuff that I've done, some customization and specific things for to be able to fuzz some of these things. So what have I done? First of all, it's an open source. So you can actually go through the source code and you can modify it, you can customize it, you can do whatever you want with it. The code base is, like I said, it's quite big. It's not a simple system, and like the Krug was mentioning, like in the keynote, is that like these systems are getting more and more complex, and this is starting to be on the verge of being a system that like one person, how easy it is to actually understand how it works. But spending some time familiarizing in the code, trying to find or trying to understand how it's creating the actual protocol data units that it's sending to the driver, I was able to figure out that there are a couple of places that you could actually tag on to and change the code so that I could actually push the packages that are supposed to go to the driver to my own message queue, and then ingesting them into Python and doing stuff with them. Why I did it this way is because I don't want to compile this all the time. So you could do it in C if you want. I mean, you can write your own stuff. This is written in C. But yeah, so you can do it straight into this source code, or then you can do stuff outside of it. I'm more proficient in Python, so I thought it's much easier to put the message queue stuff in, push all of the packets into Python, then do stuff with them, or maybe do a straight pass-through if I don't want to change anything, and then push them back to this actual code, which is then talking to the drivers and doing all of the nasty stuff that I don't want to touch. There's also a bunch of other stuff. I'll cover them a little bit later. But yeah, so if anyone has done any kind of fuzzing, you know that you're getting a lot of crashes and stuff that you need to triage in some way. And if anyone has done fuzzing on embedded devices, you know that it's difficult. Like you need some kind of feedback. So yeah, I'll cover this a little bit later, but it's basically an automated, semi-automated system to try and do the initial triage of any kind of crash, whether it's an actual crash or something else. I have also a bunch of other things here, like logging everything, storing them. I do this for both phones and for embedded devices. For embedded devices, it's a bit more complex, the setup in that for a phone, whether it's an Android phone or Apple device, you can just put a USB cable and be done with it. With embedded devices, if you're lucky, you can get some SWD or JTAG or some debugging interface, which can hopefully get you some information. Most of the time you can't, which means that you have to do quite a lot of power analysis. So you hook up oscilloscope to the system on chip that the device is running, and then you send packets, and then you capture the baseline power trace, what it should look like, and then you start fuzzing, you send new stuff, and then you compare the power trace and the difference between the power trace, and if there's wide differences, then you can sort of flag that maybe this was something interesting. Might be or might not be. I have these rigs running most of the time, and I don't want to have my screen on all the time to check up on things and maybe reset something, reset the phones or reset something on the other equipment. So I actually did some hacking on the Stream Decks. That's it's a very nice device. Has buttons, physical buttons, has nice screens. So yeah, I did a bit of hacking to do this custom stuff on the so that I can control all of the equipment in the lab from the Stream Deck and have it showing the status of the fuzzing and do a bunch of stuff. Very helpful thing if you're doing any kind of fuzzing. So the fuzzing framework, it sounds very nice and complicated and stuff. It's not. It's just a couple of hundred lines of code. Most of the code is actually dealing with ingesting the stuff, storing it, doing some triage, doing some analysis and stuff like that. The actual fuzzer part is pretty simple. It's just Redamsa with some corpus of some actual valid packets that I've sent for the devices. So this typically when I start fuzzing, I capture a lot of data how the device works in the normal state. So capturing all of the traffic, doing some analysis, trying to do some figuring out like, okay, yeah, these might be some interesting parts to look at and so on. I'm quite limited in my time and this is quite involved most of the time. So I've actually been using LLMs quite a lot over the past few years to offload some of the boring stuff like for example, for the fuzzers, I've been doing quite a lot of like giving the LLM some of this open source code for the radio access network and get it to create a Python sort of representation of parts of the protocol that I need to do some patching, for example, some lengths or calculating some CRC values or whatever. So it's quite nice to just give this massive pool of code and maybe some of the standards text like how it should be working and then get this LLM to give me a semi-working code. Of course, you need to do some stuff and fix some of the things always on it, but still, it's nice. It makes things a lot faster. As you noticed that I'm doing stuff in Python, it's not super fast. So of course it has impact on the actual performance of my network. But I mean, to be honest, I'm not running like 150 devices on the network, which are all pushing 50 megs of data through the network. So I don't care. I'm sending packets, and most of the time I'm sending 2 packets, and then the device will crash. So it doesn't really matter. Yes. So to put this more into the like what people think of like at least network diagrams or these network protocol stack diagrams is that this is actually what we're doing. So the implementation, what it's doing is that I've severed the link between the MAC and the physical layer on these the Open5GS and the OpenAir interface, and I'm capturing all of the data that is going to the lowest layer before it's going to the actual SDR driver. So I'm pushing it to my message queue, and then the fuzzer is actually consuming that. It has a couple of modes, so you can do different kinds of fuzzing, and then you have also a pass-through mode where it's basically just going to the message queue, and then the same package is put back to another message queue, and then it's ingested by the actual base station software, and then pushed to the radio, and off it goes. So, fuzzing. This whole thing actually started from a completely different perspective. I started like I wasn't initially doing fuzzing. I just wanted to be able to talk to some embedded devices that have radios. and specifically baseband radios. And the fuzzing part came much later in this sort of research that I've been doing for a couple of years now. But yeah, if anyone has done any kind of fuzzing of normal binaries or normal like PC stuff, it's quite easy. When you start fuzzing embedded devices, it's just pain. This was the initial run of the fuzzer when I got it running properly and being stable and working and got everything working. I ran it for 2 months in a row. I was basically just like, okay, I have the fuzzer running. I'm so fed up with this stuff. I'll just leave it for a couple of months and come back later and try to see what I can do. And hopefully I've created some nice crashes or vulnerabilities. And then 2 months later, I start going through the data, and I had, if I remember correctly, at that time I had 10 devices in the RF pouch. So I had around roughly 300 to 400 crashes per device. So that's a lot of stuff to go through. And the problem here is that it's not a normal like binary where you can easily start like reverse engineering it or trying to understand what it's doing. This is like a complex network of different processors talking to each other. You have the baseband processor, you have the application processor. The baseband processor is running some kind of proprietary real-time operating system. Then you have the device can be running Android or Linux or whatever. So it's not easy to understand why something has crashed. And what I noticed actually quite quickly is that many of these crashes of the communication processor happened very early on. So I would only need to send a couple of packets, 2 or 3 packets, before the actual authentication to the network, and I would already get the radios to crash. This is actually interesting, and it's if you followed the discourse around this topic, most of the research is actually done on those few first package, and the main purpose of that is because those happen before the authentication to the network, which means that anyone can start like sending those. So you like if you would be doing this in an ISP controlled network, you could actually start sending those packets before the device authenticates to the network, and this is quite a key thing. I have looked at the stuff that happens or after the authentication into the network, and there's a lot of ground to cover there as well. But like I said, from real world exploitation perspective, it's pretty like insignificant in a sense that like you can't get the device to authenticate into your network if someone is running a proper SIM card from their operator. The good thing about these first few packets is also that they're quite easy to fuzz. Like there's very little checks or things that you need to patch. So it's also from that perspective, it's quite easy. I talked about the automated crash triaging thing, and the reason why I started to do this was because it's so much work to try and go manually all of the data that I gathered. So I thought like, okay, I need to figure out some way of like limiting that data set a little bit to figure out like, okay, there are these specific errors, for example, that I'm seeing, or there's this kind of power trace that I'm seeing, that like there needs to be some specific things that I could look into and get some sort of feedback from the fuzzer and see that, okay, these events are actually interesting ones. I haven't seen them before, or there's this new error that I haven't seen. So I built this. There's 2 versions. One is for the phones, and that's based on ADB. ADB is quite nice, and actually some of the phones have these features where you can dump the communication. Most notably, the Samsung phones have this capability where you can dump the communication processor RAM and all of the logs from the communication processor. And that's actually very nice because then you can start doing pattern matching. So you're sending specific kinds of patterns to the device, and then you can actually look from the RAM dump if they actually end up there, and then start doing stuff with that. So what I ended up doing with this is that I sort of tried to figure out for every single device, and this is a lot of manual work that you have to do in the beginning, look at some sort of flags and specific errors or stuff that I think that, okay, these might be indicating that this is an interesting crash. And then get this system to flag those, get all of the metadata from the packets that I've sent, all of the PCAPs, all of these log files, anything that I can extract from the device, dump them into a zip file and put it into a different folder for sort of more manual analysis. And this brought, like, it's not super like high tech in any way, but this brought down the numbers significantly. So I was probably left with maybe 10% of the initial crashes. Yeah, so some learnings about these. So as I mentioned, a lot of these crashes actually happen very, very early on in the connection to the network. So it's surprisingly, and this is, like, for me, this was quite an interesting sort of experience as a hacker, that I've always sort of thought that these technologies, like, there's so much money put into the R&D, and there's so much effort put into developing all of these and the standards and all of the stuff, that it would be much harder to actually do this. And yeah, it was an eye-opening experience. But yeah, so it was actually very easy to crash these devices, or the radios particularly. But figuring out whether something is exploitable or not, and whether a crash is a crash, or whether it's a timeout because of the protocol, or whether it's a timeout that the device imposes when something happens, it was very difficult to tell. I mean, I have some background in mobile networking, but I mean, I'm just not that proficient with the standards or the way these should be implemented, that I could tell, okay, this 2-second time is actually because of something crashed and then it rebooted, or whether it's because this is a timeout imposed by this specific vendor in the way they are implementing the standard. And yeah, I mean, it's the something that I also sort of intuitively knew but hadn't ever verified, was that the phones are actually quite a difficult target. So even though you can crash the radios quite easily, getting and escalating your privileges and being able to run stuff on the application processor is actually quite difficult. And I mean, there's very, very good reason why Zerodium and a bunch of other organizations are still paying $200,000 for a remotely exploitable vuln in one of these phones. So yeah, there's a reason for that. Embedded devices, very different story. There's much more blind trust in this communication processor, and quite often it's actually due to pricing or whatever, or resources, or there's many reasons. It's the same processor that's running that is the application processor as well as the communication processor. But yeah, it came quite early on. It came quite evident to me that I need to get somehow the firmware. The firmware for the communication processor. Otherwise, it's just like it's black box fuzzing is good, and you can probably find stuff with it. But being able to create some sort of repeatable and figuring out why something crashed and can you actually escalate your privileges, it's very difficult if you don't have the firmware. So before we start going into the very, very deep end, it's a good time to pause and think of some of the other stuff. I mean, this is actually the stuff that I was initially looking at. I didn't really care about any of the fuzzing. The fuzzing came much later. But this is the stuff. I mean, it's very surprising that like you take any kind of device that like whether it's payment terminals or automotive ECUs or stuff that you see around us. Many of them these days have baseband processors. They have Wi-Fi, they have Bluetooth, they have a bunch of other things. Quite surprisingly, Wi-Fi and Bluetooth and Zigbees and whatnot, they are quite well hardened. So you have like, if it's a Linux box, you have like IP tables, you don't have any services exposed because the vendors are like, hey, okay, these are protocols that normal people can access. So let's do some hardening. Let's make it a bit harder. Let's disable stuff. Let's make it not easy for them to get stuff via Wi-Fi and Bluetooth. Okay, you can still do it, but it's much harder. Whereas with these, and this was very surprising to me, is that a lot of these devices, they don't impose the same limits for the LTE and the 5G or the baseband networks. And that's because it's running on trusted ISP network. No one is able to get access to that, right? So yeah, and I've found a bunch of very interesting stuff on that. And I mean, even for devices that should have been very well hardened, you still have a lot of exposed stuff on the baseband layer, and you can get access to different interesting things. Now the big thing. And I mean, I've done and looking at embedded devices for nearly a decade now, and I've never seen anything like this. I mean, before I started to do this stuff with the baseband things, I was used to looking at firmwares that were maybe like 500 kilobytes or 1 meg in size or something like that. Even that was massive. But yeah, here we come to this. I mean, we're talking about, and this is most of the time even like understating the complexity of these things. So the typical firmware is 40 megs. That's like you can't even import it into Kidra and get it to open the file because it will crash before it's processed all of the things. So I mean, there's your first problem. You get the firmware, but what can you do with it? Because none of the tools can actually open. It's too big. You have so many functions. You have hundreds of thousands of strings where like that don't have any sort of meaning to you. A lot of like standards related stuff on logging and things like that. These are I would say 99.9% of these are based on some custom or very sort of bespoke real-time operating system that is running on very complicated state machines. You can sort of like, if you go through the standards and you sort of do a bit of this fuzzing, and you can start to sort of understand how some of these state machines work, but you have very little understanding about the internal state of the device. And it's very complicated, and the way these state machines talk to each other and so on. And what has been very eye-opening experience also for me is that even though you have these very strict standards, there's a lot of stuff that is left up to the vendor. And I don't know the industry well enough to be like, don't quote me on this, but I think a lot of the like device manufacturers and the network manufacturers, they talk to each other to make sure that the phones are sort of behaving nicely, like the devices are behaving nicely, the network is behaving nicely, so that they have a common understanding that, okay, the standard actually allows you to put all of these things into the first few package, but we don't, like, you shouldn't do that. And we agree, like, under the table that, yeah, let's not do that. And then everyone sort of plays on the same rules and everything works and everyone's happy. But yeah, there's a lot of sort of things that like you can read in the standard, but you're like, hey, so it's saying this, but there's all of these like 56 other scenarios that they don't discuss about in the standard. So how has the vendor actually implemented those? And take a phone from Samsung or Apple or take a payment terminal, whatever. Everyone's implementing it in a slightly different way. I haven't come across a lot of devices that behave the same way. So one can crash completely when you send some packets, the other one is completely fine. So yeah, then there's also the customization per region, per operator, per technology. So you might have different radios. So quite often you see that they actually build a one firmware package, and then everything is included there. So the goals: get some firmwares. Try to find first, because I thought it's quite a daunting task to start reverse engineering this massive blob. So try to do some runtime debugging on the stuff. Try to find any sort of additional information around it, and then as a last sort of leg, try to do a bit of reverse engineering of the stuff to understand why a crash happens, and then last, if there is a time and if it doesn't feel too exhausting, then try to find some exploitable issues. There's two ways of in my world, there's two ways of getting this firmware. So you can dump it from a phone, or then you can dump it from a modem or system on chip. You can guess which way I took. Yeah, so phone is quite easy in a sense that you can just plug it in with a USB cable. If you have a rooted phone, you can extract it from an Android phone from the device partitions. The biggest issue I had with those, I tried that initially, and the biggest issue is that there's a lot of like proprietary packaging. A lot of the firmware stuff is encrypted or compressed in some ways. There are some pre-existing tools, and some people have done some pretty stunning work on these. But yeah, it was much simpler for me to actually start doing the other way around, actually extracting it directly from the flash. Now, it is much more work initially, because you need to get a bunch of devices, you need to extract, you need to remove the chips, and you need to reball them and solder them and whatnot. But it's actually, I learned this later on, it's actually much nicer approach, because you get the full file systems, you get a bunch of stuff that you don't get from these modem binaries, like the recovery file systems. There's typically more configuration files. There's a ton more information in all of these. And sort of one of my tricks was that I started to look for devices that are utilizing some of these same system on chips that are used in some other devices. So the biggest challenge that I faced quite early on is that a lot of this stuff is the proprietary stuff. So you have pinouts for the chips that you don't have access to, redacted data sheets, they're using customized memory layouts, there are proprietary file systems and whatnot. So a lot of sort of limitations in being able to get that. So in hindsight, maybe it would have actually been easier to just try and reverse engineer some of the packaging formats for these modem binaries. But yeah, I went this route, and so when I started to, like, my initial thought was like, okay, I have proprietary data sheets, proprietary pinouts and stuff. I'll just reverse engineer them. It can't be that hard. I mean, after like getting some of the first chips, I was spending like weeks and weeks just trying to reverse pinout for a chip that I have no idea what it is. I don't even know if it's a NAND or eMMC, and what can I use to talk to it. And then you have 162 pins on the chip, and you need to somehow figure out what it does and what it is. So I started to get a bunch of other devices. I took like devices that are completely different, like not even a phone, or like you can get some industrial barcode readers, for example, that are running some of these same chips that some of these devices are running, and yeah, they have different chips. Like they are not using NANDs, for example. NANDs are used quite a lot in these modems. So I got a bunch of those. Yeah, I was able to extract the MMC, and then I got actually a lot more information out of that, because, okay, now, hey, I see that the manufacturer of that device, which is not a phone or a modem or in fact any kind of communication device, it's an industrial barcode reader, but they have used the full SDK for that manufacturer, for that chip manufacturer. So I have actually, I could extract the NAND drivers for that proprietary NAND file system that I've been trying to reverse engineer from a completely different device. They're not related in any way, just happening to use the same chips. And the other vendor was, or the other manufacturer was a little bit lazy in like disregarding unnecessary stuff from the SDK. So they just bundled everything in, put it, I mean, there's a lot of room in that eMMC. Why not? Like we can't go through the effort of actually limiting stuff and taking out unnecessary stuff. So yeah, and then I noticed that that's actually quite a good approach. So just taking like completely different kind of devices and try to see like, hey, maybe I can get some information here, some information there, and then just like starting to build bit by bit a bit better picture about this whole device thing, and then eventually having enough information so that I can actually look at the device that I was looking at. And that was still, there was still one problem. I couldn't get the stuff out of it because of these chips. And like I said, I spent weeks and weeks trying to like rack my brain, like how can I get this stuff out of it? Like there must be a better way. And yeah, I did the lapsus thing. I just started to send people an email, like very nice, polite email, like, hey, I'm working with so-and-so device, I'm working with so-and-so people. I just lost the datasheet for this device, can I get it? 9 out of 10, you'll get a nice email back, hey, here's the datasheet, go ahead. And these are stuff like you shouldn't be getting access. Like these are meant only for the people that are actually working with these devices. Then you have that one person out of the 10 who is like, who are you? No, I'm not going to give you the data sheet. And then how you play that game is that you say like, oh, actually, I don't need the data sheet. I just need some engineer that I can talk to because I have this electromagnetic problem where something is causing some bit flips, or just come up with any kind of sobbing story that, yeah, like I have this issue that I need to debug. Like, can you give me some person that can help me? And then you go to that person and then you say like, I have this issue. Can I get the data sheet, by the way, so that I can verify some stuff? I've just lost it. And then they are like, no, I can't give you, it's redacted. And then you go to the next person and eventually you find someone who's willing to give you the data sheet. And yeah, when you get the data sheet, wow, it's so much easier. Then you can just draw a schematic, you do a custom breakout board, and then you can dump it. So it was, I can tell you, it's much easier to just send out emails than try and reverse engineer some of these pinouts. So the next thing that I tried to do, like once I got the firmware, I was trying to figure out, like I didn't want to go head on and try and like reverse engineer everything. So looking at the debugging, trying to see if there's any kind of ways I could put these sort of enable some of these debugging features. It was sort of hit and miss. For some, it was very easy. You just stick a text file onto SD card, and then that would enable anything and everything. For some, it was much more difficult. For emulation, it's just like I tried to look at it, but it's just way too complicated. And yeah, it was a hit and miss. So I mean, I was left with this, and had to do some reverse engineering. But like I said, it's too big to start manual reverse engineering. So I was actually using quite a lot of LLMs to try and get stuff out of it. So I would split the stuff into parts, stick the parts into Git, get the decompiled code, put it into an LLM, and then trying to get some of these like some of these specific things that I know that this state machine works in a specific way. That, okay, here is this part, and then try to get the LLM to find me the relevant parts. It was a bit of a hit and miss, but it makes it a lot faster to go through hundreds of thousands of functions in a code. And yeah, that was very, very nice. So then we get to the final part, which is I've been looking at this for many years now, and it's very easy to get blindsided. So I thought I'll put my money where my mouth is and do a proper demo for this talk. So I went to the nearest electronics shop, get a phone that I have that has a system on chip that I have absolutely no idea about. I've never even heard of this Unisoc, whatever Chinese manufacturer. Patch everything, stick it into the fuzzer, and see how long it would actually take for it to produce some stuff. And yes, it wasn't that long. So here in the left-hand side, you have the packets that are when I'm behaving nicely, so when everything works normally, and then there's some fuzzed stuff. And you can see that the difference is like here, for example. This is a mishandling of some specific property in this is I think the second packet that is sent to the device, and I'm just changing 2 bytes. I mean, it's not really that complicated, and doing some triaging of this. So I actually went and looked at the relevant parts in the standard for all of this. So this is actually valid from the standard point of view. So we are releasing some data radio bearer. So the DRB is a property that is it's basically setting up a channel for the data channel between the device and the base station, and yeah, so it's setting it up. It's releasing it when it's not being set up yet. So we're releasing something that has not yet been set up, but according to the standard, it is completely fine. And yeah, if you do it later in the chain, the baseband is not crashing. So it is something that the vendor hasn't implemented properly because we're not following the actual rules. Well, we're following the actual rules, but we're not following the sort of unwritten rules of this. And same thing continues. Like this, another similar thing. We're setting up and releasing stuff at the same time. We're putting up new properties. This is a bit more changes on the actual packet. But here, same thing. It's completely valid according to the standard. But like we are setting up and releasing stuff at the same time. It shouldn't be done at this part of the chain. And what was interesting with this one is that this is actually persisted after reboots. So you need to actually take the SIM card out to properly reset the radio to be able to actually get rid of this. So it's crashing it so badly that even rebooting doesn't work. And I mean, it just kept on continuing. And I had the fuzzer running for 2 weeks, and like to be honest, I wasn't willing to go any further just to prove a point. But I'm pretty sure that you see where I'm getting. So then verifying stuff. It's difficult. Like I said, the state machines are complex. You don't know entirely what the state of the device is and when it's working. So I could verify and repeat some of these, but I mean it's this first one, for example, it was only like I could only get it to crash when that specific ID, the data radio bearer ID, was being used later on. So it could take a day, or it could take 5 minutes, or two minutes, or whenever that was used. It might be nice, or it might be very unstable from exploitable point of view. Then the second one is quite a bit more interesting in the sense that it's very sporadic. Like I couldn't quite figure out like why it's so sporadic, but it's actually crashing something also on Android. So there's this IMS handler that is handling some of this voice call stuff for Android. So it's actually crashing that also. Not always, but most of the time. So this would be a very good candidate, for example, to do some further work on the Android part and trying to get it to be a sort of more exploitable. But yeah, all of these require reverse engineering, and we're looking at 40 meg firmware. So then we run into this issue. I mean, if you're familiar with the 5G HAL stuff that was released not long ago, I mean, their team is massive. I'm doing all of this by myself. So I mean, I just don't have the resources and time to go through all of this. Now, this wouldn't be completed without stuff that literally no one talks about, which is the actual exploitability of these issues in ISP run networks. And I mean, I've shown you that you can do this on very small budget, but when we get here, we start to get into the budgets of the three-letter agencies. I mean, in the real world, you have Doppler shift, you have noise, you have all of these other radios that are talking there. Then you need to jam the radio to get it disconnected, and there's a whole lot of stuff. So it's not as simple as you think, and this is exactly, I think, why a lot of this university work that is happening in this field is a lab stuff. And in the ISP attacks, you're actually limited to only of those couple of packets that are happening before the actual authentication into the network. So, some final thoughts. This is roughly where the time has been spent on this thing. I mean, getting everything set up, that's easy. Building some of the fuzzer stuff, that's easy. Then once you have the fuzzer and you have a working network, then it gets hard. Then it's starting to be a time vampire, as I like to call it. It's sucking up all the time and effort that you have, and you can keep on going and going and going. And this is like my one-person part-time effort of doing this. This was initially supposed to be a sort of catalyst for the upcoming T2 talks. Like here's a lot of topics that haven't been covered with, but yeah, that's not. But yeah, here's some interesting stuff that you can look and submit talks to other conferences if you like. But yeah, so the final conclusions is that, I mean, like Tom was mentioning, you don't need to be a three-letter agency anymore to get into this game. It's actually quite affordable. Yeah, it's still like hundreds of euros, but like we've gone down from hundreds of thousands of euros to hundreds of euros. It is very, very easy in my experience to do a denial of service attack against any kind of baseband device, but getting this like properly exploitable issue that you can actually escalate your privileges into something else is much more difficult, and that will require either a team or a lot of time. But yeah, I mean, this has been an eye-opening experience to me in a sense that like it's very sort of new thing because these capabilities haven't been around so long. But yeah, I mean, it's quite evident if you followed some of these things that are coming out from the recent war zones or the conflict zones, is that like some of this stuff is actually quite widely being used, and specifically because the radios, for example, they are so cheap, and you can find a lot of this stuff. So I mean, if the good guys can do it, so can the bad guys. And that's, I think, why we should be, like Tom said, like why we should be spending a lot more effort in the future to think about these issues in broader terms. That's it. Questions?
Thank you, Janne, for the interesting presentation. So you had 2 0 days that you called denial of service.
Yes.
How did you convince yourselves that those are like just denial of services?
I don't know.
The second one, like, are you convinced that it's not a use after free or something?
I don't know. I just didn't like. This was the purpose. Is like I time box. I put 1 month of time and see what I can find and try to prove myself that this is actually easy and doable. So yeah, I don't know. I didn't do more reverse engineering on these issues, and I mean it could be something completely different. It could be much bigger issues, and it was actually much more than just two. I just didn't go through. They were very similar to the others. But yeah, I mean, I don't know. That's the thing.
Sounds like we'll hear more at Black Hat.
Just wondering on the crashes, was the device able to recover?
No, most of the time not. You need to well, I would say roughly 60% of the time reboot is enough, But then you have the rest of the 40% of the time is that you need to actually like physically take the device out of the cage and then take the SIM card out, because that seems to be the only way to properly reset the radios. And I was actually thinking more recently that if you do this on eSIMs, like how can you like is there a button on the OS to reset the radio? I don't know. I mean, if someone knows, then please enlighten me. Because in that case, it's pretty bad because your phone is toast after that.
Okay. Did you try to emulate the firmware to get some sort of guided fuzzing or something?
Yes, I tried to do parts of it in Kimu, but it's like there's so many, like everything is proprietary. You don't know the address ranges for most of the peripherals and stuff like that. So it's just way too complicated. Plus the stuff and the formats and the way they are talking to, for example, a DSP, like a lot of these state machines, like you need to have specific peripherals set up so that they would even work. So it's just like there's some work that has been conducted on it, but it's just like it's way out of my area of expertise.
Hey, thanks for the presentation. You mentioned that on iOS and Android, you saw that the segregation between the CP and the OS was pretty good. Could you elaborate a little bit on that? What kind of designs or controls you saw when looking at it?
Yeah, so the main, at least on Android, to be honest, I haven't looked at the Apple devices that much, and purely because it's much harder to get stuff out of them than from Android. But on the Android, there's actually quite a few layers of stuff that is like there's a lot of inter-process communication things, and there's a lot of different APIs. So the communication processor is actually talking to some other API on the OS side, and then that is talking to another API and another API. So there's a lot of like layers in between. So being able to get that like code execution, for example, on the on the application processor means that you need to craft a packet that actually passes through all of these layers, then ends up somewhere else in the. And this second one, at least from the crash logs, I mean, it could be something that is causing some effects also on the OS side.
All right. Next up, lunch. Thank you.